Assalamualaikum warahmatullahi wabarakatuh. My name is Norazira binti Azhari. So for the introduction, this project explains the implementation of interpolation method in engineering by developing the method statement that is required to resolve the exploitation interpolation method. So our problem statement is based on slab, which is slab is common structure in the building. Slab can be recognized as a plate element that will form floors or roof in the building where it carry uniform distributed load or lateral action. So in designing slab, there are several requirements and steps needed to follow. All procedure and criteria in designing slab is based on error code 2 that can be applied for both one-way and two-way slab. So both of these slab using bending moment coefficient in order to determine the moment that occurs on the slab. So the bending coefficient can be found by using table 3.14 and 3.15 in the Eurocode 2. So there are certain value was not available in the table and needed to interpolate to find the exact value for bending coefficient. So in this project, the implementation of numerical method was used to find the bending coefficient value that is not required in the table. The objective of this project is the first one to solve the problem statement by applying numerical methods with Lagrange Interpolation. The second one to identify the suitable value for bending coefficients for slab that not state in the table from Eurocode 2. The third one is to apply a suitable numerical method that able to find the slab bending coefficient value by comparing conventional interpolation and Lagrange Interpolation method.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Nasrantasha and I will present for question and fill a table. For the question is, during the construction, slab and beam are cast together. So the dimension of slab is 5 meter width and 4.42 meter length. Slab is known as restrained slab, where continuous and discontinuous edges exist. The finishes, shielding and surfaces form a characteristic permanent action of 1.5 kN per meter square, which is excluding safe weight. So the characteristic variable action of is 4.0 kN per meter square. So find the suitable bending coefficient of slab, then calculate the moment. Okay, so for the filler table, for the first one is the fact is the shape of the slab. So the idea is shape of the restrained slab is rectangular. So the learning issue is how to determine the slab distribution. So we can find it the slab distribution by using formula Ly over Ls less or equal with 2. So for the second one is a restrained slab have bending coefficient. So the idea is finding the bending coefficient, which is beta x and beta y using data in the table given. So the learning issue is how to determine the bending coefficient, which is beta x and beta y if the value not stated in table. So we can use Lagrange interpolating polynomial formula, which is Pn equal with L naught times function of x plus Ly function of x times with function of x. So the last one is a restrained slab have moment. So the idea is finding the moment of slab using bending coefficient. So the learning issue is how to determine the moment of restrained slab. So the action is we have to use formula MSX equal with beta x times with n and times with length the power of 2. Same goes as y, which is MSY equal with beta y times n times with length with the power of 2. Okay, so for the determination of slab span ratio, which is the formula is Ly over Lx. So Ly is 5000 mm over with Lx 4420 mm. So the answer is 1.13, which is smaller than 2.0, and it shows that the slab is two-way slab. Okay, so next for the finding the bending coefficient by using conventional interpolation method. So there are two types of moment. The first one is negative moment at continuous edges and positive moment at midspan. So for the negative moment, which is 1.2 minus 1.1 over with 0.063 minus with 0.056 equal with 1.13 over minus 1.1 over with x minus 0.056. So x will be 0.0581. So next for the positive moment at midspan is 1.2 minus 1.1 over with 0.047 minus 0.042 equal with 1.13 minus 1.1 over with x minus 0.043, and then x will be 0.0435. Okay, next for the calculation for the bending moment. So the first one is for negative moment at continuous edges. So this negative moment is m as x1 equal with beta x times nd times length lx the power of 2. Conventional, we will get 0.0581 times with 13.09 times with 4.42 the power of 2, and we will get 14.88. Next, for the positive moment at midspan, the formula is the same but the value is different for the beta. For the last one is conventional, which is 0.0437 times with 13.09 times with 4.42 the power of 2, and we will get 11.12 kilonewton meter.
Hi, my name is Application of Numerical Methods, and I will present how to calculate the bending coefficient that we use in the formula of the moment at continuous edges by using the Lagrange Interpolation method. Okay, bending moment are acting on the slab, which is the continuous edges, and we need to calculate the time as x. Okay, this is the table of the bending coefficient that we can get in the UNIVERSITI. Firstly, before we can get the value of the bending coefficient, we need to calculate the section ratio, and the ratio is 1.12. But these values are not in the table, so we can use the Lagrange method because we know the 1.12 is in the between of the 1.1 and 1.2. So this is the formula of the Lagrange Interpolation method. There are 4 types of the approximation. First is the linear approximation, first order. For the full approximation, second order, cubic approximation, third order, and lastly is the quartic approximation, fourth order. Okay, so now I will show you how to use the formula of the Lagrange interpolation method based on the table of the bending coefficient. So, firstly, unit approximation, first order, you need to use two data, that is 1 and 1.1. So, we get 0.0587. Next is quadratic approximation. We need to use three data, that is 1, 1.1 and 1.2. So we get 0.0581. Next is the cubic approximation. We need to use four data, that is 1, 1.1, 1.2 and 1.3. And we get 0.0583. Lastly is the quadratic approximation. We need to use 5 data, that is 1, 1.1, 1.2, 1.3 and also 1.4. And we get the answer is 0.0581. Okay, so after we get the value of the bending coefficient based on the slab ratio 1.13, so we can proceed to calculate the bending moment at the continuous axis, and this is the formula that we will use to find the bending moment. Before that, we need to know the information. So this is the information, and this is the load extreme on the slab, 13.09 kN per meter square, and x is the shortest length of the slab, 4.42 meter, and the coefficient that we calculate before using the Lagrange Interpolation method. Okay, so based on this formula, we can get the bending moment. Linear approximation, we get the 15.01 km/meter. Quadratic approximation, the answer is 14.88 km/meter. Cubic, we get 14.91 km/meter. And lastly, the quadratic approximation, the answer is 14.88.
Hi, so we are going to determine the bending coefficient at the midspan, and then we will calculate the bending moment acting on slab. So sagging moment acting on slab, the location is as shown in the figure, which is denoted as MXX1. So the slab span ratio 1.13 is not in the table, but we know it is between 1.1 to 1.2, so we can use Lagrange interpolation method. So Lagrange interpolation method, we use four types of approximation, which is linear approximation, first order will pass through 2 points, quadratic approximation, second order will pass through 3 points, cubic approximation, third order will pass through 4 points, and lastly quadratic approximation, fourth order will pass through 5 points. As for linear approximation, it used 2 points, so from I0 to I1, substitute the value of x and y in the equation. So P1 is polynomial of degree 1, 1.13. The answer will be 0.0438. For quadratic approximation, polynomial of degree 2, 1.13, use 3 points from 0, 1, and 2, so we substitute the value of x times by the value of y, so we total up and the answer will be 0.0436. For cubic approximation, P3 is polynomial of degree 3, 1.13, using 4 points, so from 0, 1, 2 and 3, so x times y, this is the value of y. So we total up and the answer will be 0.0437. And lastly, quadratic approximation, P4 is polynomial of degree 4, 1.13, used from 0, 1, 2, 3 and 4, since it was to 5 points. So the answer will be 0.0436. So bending moment at the midspan, the equation is M moment equal to beta is bending coefficient, ND is the design load given in the question, and the LS is length of the shortest one, which is 4.42 meter, and the design load is 13.09 kilonewton per meter. For the linear approximation, the bending coefficient is 0.0436, so the moment is 11.2 kilonewton meter. Quadratic approximation with the bending coefficient of 0.0436, the answer for the moment is 11.15 kilonewton meter. Cubic approximation coefficient of 0.0437, the moment acting on slab is 11.18 kilonewton meter, and last one using quadratic approximation value of bending coefficient 0.0436, the moment acting on slab is 11.15 kilonewton meter.
Hi, I will present about the error and conclusion. For error, there are two, which are error of bending moment coefficient and error of the bending moment value. So the first one is the error of the bending moment coefficient. There are two places that we need to find the bending moment coefficient, which are positive moment at midspan, and the next one is the negative moment at continuous edge. We use the Lagrange method, which are linear, quadratic, cubic, and quartic. So, as using this Lagrange formula, we got the value stated here. As for the error, we using the absolute error formula, which is exact value minus Lagrange value. So, got the value stated here. The error of the coefficient value compared with Lagrange method, different error is below 0.005 except for the linear approximation at negative moment. Next, for the error of bending moment values. So it is the same procedure as error of bending moment coefficient. We still need to find the value of the bending moment at the positive moment at midspan, and also negative moment at continuous edge. So we also use the Lagrange method, which are linear, quadratic, cubic, and quartic, and get the formula stated here. As for the error, we are also use as same as the error of the bending moment coefficient, which is using the absolute error formula, which is exact minus with the Lagrange value, and we produce the value here. It is known that exact value for the positive moment at midspan MSX1 is 11.12 kilonewton meter, and the exact value for the negative moment at continuous edge is 14.88 kilonewton meter. The error of moment value compared with Lagrange method, different error is below 1.0 kilonewton meter. For conclusion, we can summarize into 4 categories. So for the first one is the method. Lagrange interpolation can be implemented in finding the value for bending coefficient slab that was not stated or provided in the table from the Eurocode 2. Next, the bending coefficient. Error difference value was below than 0.0005 to conventional value. Next is moment. Moment value at on the slab different below than 1.0 kilonewton meter had no effect on the stress of the slab. And lastly is the implementation. Lagrange method can provide the value in range. The implementation is suitable depending on the situation and limitation during the design phase. That's all from us. Thank you.